Thank you, Andrew, for kind words. Good morning, good afternoon, good evening for everyone who is joining the the last day of the conference today. It's 7 p.m. here in Kyiv in Ukraine, and let's start the day with a keynote. So, data is a new security boundary. As Andrew mentioned, I work at Kozak Labs as head of customer solutions security software engineer. So at Kozak Labs, we do data security. We work on sophisticated technologies around cryptography, right? So please take everything that I will tell today here with a grain of salt, because I am into security world, I am into cryptography world, so I see everything from, cryptographic perspective, right? For example, we often, at Kozak Labs, we often build tools and solutions to protect data where it's the most vulnerable, in applications, in novel technologies. I won't talk about any commercial solutions, but we have a lot of open source, and as Andrew mentioned, I'm maintaining the open source library CMIS, which is a cryptographic library, by the way, and recently learned that it's recommended by OWASP, MSTG, and the funny thing, it was not me who put it there, so yeah, I was like, yay, okay, to set expectations correctly, because this is a cryptography talk, at least data security talk. The things we won't talk about today. We won't talk about exact ciphers. We won't talk about symmetric, asymmetric encryption. We won't enumerate typical mistakes developers do. Well, developers do a lot of mistakes, and only recently I've seen again issues with null IV vector for IS-CBC. So all these not for today. We won't talk about TLS. We won't talk about privacy. We won't talk about fear, uncertainty, and doubt. So no breaches, no incidents. We also won't mention or names any exact tools that you can use as a silver bullets to make your life easier. No. Today we're gonna look on data security and cryptography from architecture perspective. What is it? Why we use that? How to use encryption? How to build in complicated encryption workflows into your architectures, into your apps. And I will show you several real-world examples, several observations I made where companies integrated encryption and security together with other security controls for data encryption. So I hope you're ready to continue, finish your day with data security talk. By the way, some things I will mention, please take a look at the schedule, because we do have another talk today regarding data security and encryption. So if you are into this space, I recommend you after my keynote to go to that talk. I believe there are two speakers from Ubik company, from Ubik Security. Okay, let's talk about data security one-on-one. What is the world we live right now? The modern infrastructures. What I see that the applications are becoming more and more complicated. The infrastructures, ecosystems are becoming complicated. Often, even within the same company, different teams select different tools or different databases to build their part of the application, their part of the product. And I've seen companies where different teams selected each of them different database within the same cloud. And when they asked people like me, hey, Anastasiia, how to secure data in all these? What I do is like, oh my God, let's start with the data flow first. Let's start to understand where you put your data, why you use all these databases, why you use all these public clouds, why you put all your data in these third-party APIs, integrations, and BI analytics tools. Because the world is moving to no perimeter, and we are moving to the zero trust things, zero trust architectures, right? So this is what it looks like from my perspective when we are talking about data in a modern architectures, in a modern products. And that's why this is the topic of my keynote. That's why I'm saying that today, data security is not let's protect data where it's not. No, it's let's protect data whenever it exists. Right, so data security measures become a security boundary for data, and if your company values the data, basically these data security measures become a security measures for your company as well, right? Not depending on the cloud databases, not from location perspective, from data perspective. And every data flow, simplified in a simplified way, has only a couple of steps. The data gathering, where the data is gathered, what is the user input, or data is generated, or data is derived from. Data processing, how data is being processed, right? All these calculations, analytics that you do, how you store the data, how you back up the data, how you send this data to others, fortunately for authenticated users. And data output, this is the tricky part, that's because the data should be removed at some point in the future, right? Because the data might be migrated into different databases. And of course, we have this bunch of third-party tools that we push our data into, like all these log analytics, all these CMs, all these BI tools, yada, yada, yada. And on every step of this even super simplified data flow, the troubles might happen. Bad data gathering, well, without consent, right? Most issues happens with data processing, leakage loss, disclosure to unauthorized users, and of course, tons of things happening with output step. I've seen products that don't remove data at all. It just goes somewhere. I've seen also, by the way, a lot of examples where data is stored securely, like encrypted, but the backups are plain text. So typical data security looks like that. Very simple 5 steps. Looking on any product, looking on any architecture, you try to identify the sensitive data. In many cases, there is not only one type, but a lot of types of sensitive data, right, with different risks and threats to that. You try to map the data flow, which components this data goes through. Do these components need access to the data in plain text? What are the risks for these components? What are the risks for the threats? You do threat modeling. You build risk and trust models. You try to understand risk impact. And when you understand all that, when you map the data flow, you try to select, select, or design, and then, probably implement proper security controls around data. That's super easy. That's all the steps I do every time someone asks me, hey, we have this and we need to protect the data. Yeah, I know. This may sound like let's draw an all. Yeah, only 5 simple steps. From my experience, the first 4 with identification, with prioritization, risk and threat modeling, it might take weeks, depending on the scale of your product or your project. But the last step where you select and then implement security controls, this could be months, it could be years, it's like a continuing journey. So this is like a data security 101. Let's move to the ultimate part of that, right? Because I assume that everything here for now is easy for you. Let's go deeper. Encryption. I like to say that encryption is an ultimate data security measure, just because when the data is properly encrypted, it cannot be unnoticeably suddenly decrypted. The trick is properly encrypted, okay? When data is encrypted, it's protected from insiders and outsiders. And what is as I have software development background, for me, probably the best output from data encryption, from encryption in general, is that when encryption is properly implemented, my team, developers, can make mistakes in other pieces of the infrastructure of the product, but those mistakes won't affect as much. Because even in case of the incident, in case of the breach, the data is still encrypted, So yeah, I'm not saying that it's good, but I'm saying that in many cases, I've seen examples where even when the incident happened, when the data was encrypted, the damage was quite limited. I really like encryption. And of course, this is pragmatic, security engineer perspective. And of course, we do have a lot of regulations, compliance, and requirements. For example, I really like to say, to show this one from Department of Defense, 10 Commandments of Software. Number 9 says, data should be always encrypted unless it's part of active computation. Then, of course, GDPR. I won't dig into, I know that you know. In GDPR, there are articles that explicitly say data encryption. You can open GDPR articles, you can Google, you can put there search encryption, and you will find, yes, GDPR is data privacy regulation. These are the regulations about like human rights, right? They don't define how exactly you need to encrypt the data. They just say state of the art, but still, they do say data encryption. And of course, we have a lot of more, many more regulations that do classify data from sensitive and personal. So they provide you with data types you should keep an eye on. And often they recommend or they require some kind of data security and data encryption, anonymization, tokenization, many more. You know all of these, you know, like HIPAA, FISMA, FIPS, FedRAMP, CCPA, many more. If you're curious, many of my slides have like additional information, lots of links. And once this video will be available for everyone, I will make my slides available so you will be able to click on these links. Because yeah, there is a lot of content that I want to press into this talk to spend more time on interesting things and less time on regulations. Let's start OWASP. Again, this is a OWASP conference, so I'm sure that you know about new updated OWASP top 10, right? So let me put two small accents. Cryptographic failures. Cryptographic failures become number 2, right? So it's getting up as the most as the typical mistakes of the typical risks many applications have. So cryptographic failures in a OWASP top 10 is focused mostly on cryptographic usage and issues with implementation, right? Which includes selecting unsuitable, how I say, like unsuitable cryptographic controls, cryptographic primitives. I often see, you know, base 64 instead of encryption. Yes, it's 2021, but still we're still there. I see how hash functions, typical hash functions are being used in places where password-based KDF should be used. I've seen examples where the wrong, maybe inappropriate, not wrong, but unsuitable, inappropriate IIS mode is used. And of course, let's not go into key management because still I see applications that generate cryptographic keys using mass random, right? Another accent in OWASP top 10, another like topic is insecure design, which is number 4, which also is a new like category like that has, it's a new category. Well, it's not new, it's like reworked category, which focuses on design and system architecture, right? So if cryptographic failures are focused on implementation, insecure design are more like a design point of view. What is interesting for us in this insecure design section, that from data security perspective, what we often see is that there is no data security, right? So like missing security controls. There should be encryption, there is no encryption. There should be some kind of anonymization, tokenization, none. Then we often see misused security controls. You know, encryption just because we encrypted data somehow and we feel good because the data is encrypted. But once you start looking in, you see that, yes, data is encrypted, but, you know, encryption keys are stored together with encrypted data. Or it's been encrypted in a wrong place. It's been like decrypted in a wrong place, things like that, right? So from design perspective, when you look on the data flow, when you look on the components diagram, and of course, a lot of homebrewed encryption protocols are falling into this category. When you see developers try to re-implement double ratchet, for example, why? You know, things like that. Just because, yes, encryption is complicated, cryptographic protocols are even more complicated because there are a lot of things to keep in mind. And let's continue with OWASP. You can find a lot of cryptography-related and data security-related requirements in OWASP ISVs, which are placed mostly in chapter 6, 8, and 9, right? A lot of them. And you can find some of them in OWASP MSS mobile application security verification standards. They are placed into chapters 2, 3, and 5. This is on screenshot. You can see the chapter 3 with like MSTG crypto. And as I know, MSS and MSTG are being refactored right now. So we can see maybe in future we will see even more requirements regarding data security. However, so there are a lot of things, right? There are regulations, there is like OWASP requirements, tons of requirements from MSS, some from ASS, some requirements from MSS. But this is only the tip of the iceberg when we are talking about data security and when we are talking about encryption. And let's go deeper. I hope you would like that. Now, because now the interesting part will start. Let's talk about encryption, but not about ciphers again. We won't talk about ciphers. Forget about elliptic curves and math and elliptic curves. Let's talk about infrastructures. Let's talk about data flows. So there are different kinds of encryption, and many people that don't work with encryption confuse them, which is okay, because there is no like the single book that says this is the only right way. Let's put some emphasis, let's put some accents. When we say data at rest encryption, we mean that data is encrypted when it's stored, right? It could be file system encryption, operating system encryption, file-based encryption, database encryption. Like, modern databases, they have this checkbox, yes, encrypt data when it's stored. Then transport layer encryption, data in transit. Well, obviously, TLS and things like that. This is not a topic for today keynote. Today we will talk more about application level encryption. And again, I recommend you to check the next talk after this keynote about application level encryption. I haven't watched it yet, but I've seen according to the description that guys will go even deeper in these topics. So what is application level encryption? It means that some application is responsible for encrypting and decrypting data, right? The trick here is that application level encryption should work with both data at rest and data in transit. It means that your application can encrypt the data, right, in the application code, then send this encrypted data to some other application. And of course, when you send it, you use TLS, right? Then the other application gets this data and, for example, sends this to the database. And in database, you will use data at rest encryption. So application level encryption will work together with all the current types of encryption you use, right? What I'm saying that you should not stop using TLS if you will start encrypting data inside your application. Okay. The tricks with application level encryption is that if it's application controlled, it means that application will control key management as well, and this is where it gets complicated. Let's go in. As one of the examples, because people usually confuse, as one of the examples, here I compare two things that we shouldn't probably compare. It's TLS and application level encryption. You see, TLS protects data from server, from application, from operating system to operating system, I'll put it this way. Application level encryption allows you to build code inside the application, right? So it moves boundaries closer to the application process that actually needs this data in a plain text. Now, I just say application. Depending on your use case, depending on the architecture, application can be different. If application level encryption happens on the client side, let's say mobile applications, you can say client side encryption, server side encryption, proxy side encryption, whatever, depending on your use case. Now, application level encryption doesn't mean that all the data is encrypted. Typically, we say about field level encryption or selective encryption, right? So we don't want to encrypt them all. We don't want to encrypt everything. When application sends some data to the other application, for example, in JSON. For example, this is a huge JSON model. The application can select what, well, you select as a developer, as a security engineer, what types of data is sensitive and what data is sensitive and what types of data should be encrypted. So you build in this encryption code, so application will encrypt the data, only these fields before sending it, right? Another topic here is end-to-end encryption. We can say that end-to-end encryption is a subset of application-level encryption. The trick with end-to-end encryption, that the main idea that the data should not be decrypted like in the middle on your server side, in your like cloud, in all these components. The data should be encrypted and decrypted only on your ends in the infrastructure. In many cases, these ends are mobile applications, but it's not like required. It can be like any application. You can just say that, okay, this part of my data flow is end-to-end encrypted. The trick here, as I mentioned, that all the intermediates, all the components the data goes through, they don't have access to data in plain text and they don't have access to keys. So they cannot decrypt the data. End-to-end encryption is great. You use end-to-end encryption basically daily if you use some of modern messengers. The thing here is that if data is end-to-end encrypted, it doesn't mean that all data is end-to-end encrypted, and it doesn't mean that the application is secure, and it doesn't mean the application won't sell your data, right? Because we see in the real world that applications can analyze your data first, like sell it to third parties, and then only encrypt it and proudly say we use end-to-end encryption. So it's just a technology. I know that you like to compare, to look into threat modeling. So let's compare TLS and application level encryption. They are different techniques. It's like comparing apples and oranges. It's unfair, but we will do it. I really like to show this table as a comparison table because it has different encryption ways, different techniques. You see like TLS, data address encryption, database or like transparent database encryption, application level encryption, and end-to-end encryption. And it has different threats or like events that can happen. And you see that different encryption approaches protect from different classes of events, right? So in some systems, and of course, what to use depends on your threat model. In some systems, that's totally fine to use TLS and data address encryption and you're okay. But in many, many cases, especially those cases I will show you a little bit later, you are pushed to use application level encryption or end-to-end encryption. Because, as I mentioned previously, when the data is encrypted, it cannot be magically, suddenly decrypted. And this is what it makes good. However, application encryption is so great, right? Why not to use it everywhere? Okay, here is the trick. It's great, but it's a little bit complicated. When I say a little bit complicated, it means a lot. Like it's really complicated, especially for developers, especially who know nothing about cryptography, because application level encryption means that it should be somehow related to the application, right? It's either the code in the application or some library or some SDK or some service that the application talks to. But in many cases, developers have this exposure to encryption, and things get complicated. I also like to tell that application level encryption or end-to-end encryption, they are great until you think about key management. All the NIST special publication 80057, all the key management process, because often when we think about encryption, we think about key management, we think about key generation, key derivation, right? But there is much more than that. Key storage, obviously. much more than that, like key rotation, revocation, expiration, deletion, rotation with re-encrypting data, rotation with without data re-encryption, you know, sharing keys, different key escrow schemes, all the key management. This is where all the fun is and all the issues are. And of course, key backup. Oh my God, I've seen so many stories where like products have application level encryption or end-to-end encryption, and everything goes okay until someone loses the main key, you know, or someone loses the access to KMS that stores its main key, and and this is, yeah, this can be brutal. Okay, let's mention some other nice concepts that will help us today. First is zero trust or zero trust architectures. Yeah, it's a little bit of a hype. We know that this term is just a hype term, but the idea is pretty old, right? It basically is the assumption that in our infrastructure, in our architecture, components, our services, they don't trust by default to each other. No, they verify, they authenticate other components, even within our network, right? The idea is not new. I believe that zero trust, like fight me, but I believe that zero trust is more about access control and authentication, and it has almost nothing to do with encryption. There is another concept here, zero knowledge architecture. When zero trust is already like published, the term is defined. You can see NIST guidelines about that. With zero trust, zero knowledge architecture, it's not as simple. The term is a little bit vague, I will put it this way, because we also have another very similar term, zero knowledge proofs protocols, which are cryptographic protocols, right? So zero knowledge architecture, it's not so widespread. They also can be called no knowledge architecture. The idea is here that your system operates on data without having access to plain text. So only encrypted data. And only those components, the people or like services that require access to plain text data, only they have some means access to keys to decrypt this data. All the other components just have no clue. It's just binary. What helps us to build zero knowledge architectures is, of course, end-to-end encryption and authentication and different nice cryptographic techniques that allow you to compare data without actually like revealing it. All these protocols I mentioned previously, zero knowledge proof protocols, interactive, non-interactive, all these password protocols like PATE, PACE, yes, and OPAC, and all the cryptographic like encryption ways, new cryptographic approaches like homomorphic encryption, fully homomorphic encryption, or like searchable encryption. So there are already a set of protocols that allow you to build systems where a system operates on encrypted data without having access to plain text. Of course, it comes with cost. One of these modern and prominent ideas is searchable encryption. Again, not new. Nothing is new in cryptography. We just see reincarnation of the old ideas every like 5 to 10 years because we have better technologies to handle that. So searchable encryption is the idea that you can perform queries on encrypted data without actually decrypting them, right? So search through data without decryption. There are many schemes available. Symmetric searchable encryption, public key encryption with keyword search. As I mentioned previously, homomorphic, fully homomorphic encryption. One, from my perspective, again, fight me. From my perspective, the most realistic approach in the searchable encryption right now, the most production-ready approach is keyword search, where you can search where you have encrypted data and you have a query, a keyword, and you search the database in this keyword. This is very useful when you have some encrypted personal data like emails, encrypted emails, and you can search by email and all the data will be encrypted, but you can still match the user by email, even when all of this is encrypted. So there are different approaches possible. I know a lot about one approach is like we use, and we published, did some research and published some papers, which is known as blind index. It's based on hashing. But also there are approaches using deterministic encryption. Okay, now we start getting deeper, right? You see, we start getting deeper into our iceberg of data security. But I hope, I don't see any feedback, but I hope you're doing well over there. So I will show you one more slide here, very interesting one. All the things I described previously, they are, well, pretty, I would say, industry proven and ready, but in cryptography we have a lot of exciting things. For example, all these SMPC, Secure Multi-Party Computation Protocol, the whole set of protocols that allow you to build products, like it's used this umbrella term, privacy enhancing cryptography, which means that you can build a product and you can do all this analytics from your data while respecting and protecting user privacy, right? If you know the term differential privacy, so differential privacy systems are often, not always, are often built using these privacy enhancing cryptographic technologies. So secure multi-party computation, private set intersection, private information retrieval, homomorphic encryption I mentioned before, PACE or PAC I mentioned before, right? Then zero knowledge, the whole set of zero knowledge proof protocols, which have a new life, I would put it this way, with cryptocurrencies, right? Because previously only interactive zero knowledge proofs were popular, and now we have a lot of non-interactive zero knowledge proof. They're very simple idea, very simple, behind zero knowledge proof protocols is that when you have two parties and they share the same secret, you can compare, these parties can compare the secret without revealing it, without sending it to each other, right? So they send something, they send some derivatives from the secret. And with interactive zero knowledge proof protocols, they require several steps, several hops to send several bits of information to send to each other to verify, to make sure that each of these parties has the same secret, right? In blockchain and cryptocurrency world, we see a lot of zero knowledge snarks, zero knowledge Starks protocols. For example, many zero knowledge snarks, they are non-interactive, so they allow comparing something with only one hop. Okay. Let's talk a little bit about data structures. As I mentioned already, cryptocurrencies, let's talk about blockchain, but not like blockchain, but blockchain from cryptographic perspective. What I see right now that these modern data structures like blockchain, like Merkle trees, well, modern. Again, math is not modern. These data structures are based on math designed in 60s, 70s, 80s. So I see a lot of applied products that use these data structures. Why? For example, for audit logging. So imagine that your system produces logs, right? Audit logs, which mean that who has access to something, when it happens, audit logs. But audit logs are sensitive data. You want to protect those audit logs. So what you can build, you can create a data structure. You can put these logs into special data structure to verify that no one had tampered these logs. One of these data structures is a blockchain in sense of chain of blocks, hash, like you calculate hashes of the content of previous block, yada yada, blockchain. Another very used data structure is a Merkle tree, also a tree with hashes, like a tree of hashes, if you can put it this way. If you put your audit logs into these data structures, you will notice if someone will try to change the content of log, or if someone will try to delete the whole log message. Just because these data structures allow you to verify by computing hashes that everything is in place. And by the way, Merkle tree is also used in CT, in certificate transparency. So not super new, not super modern. And the last bit here is post-quantum cryptography or quantum safe cryptography. I won't get into details on that. If you're curious, please check. Jean-Philippe Thomasson does a lot of talks about this topic, and I really like the blog post from Cloudflare from 2 years ago, I believe, when they put post-quantum key agreement protocol into TLS and measured the results. So all this modern cryptography, they're like monsters in this iceberg. I mean that, yeah, there are a lot of tools, they're nice and they're modern and we like them, but they're probably not all of them are like production ready. So, but we will get there eventually. Let's talk about simpler things. Because cryptography never works alone, right? Cryptography should be surrounded by a set of traditional security controls, how I call them. We have the data, which the data should be encrypted in storage, the access should be protected, everything should be logged, all the sensitive actions, right? All the errors should be logged. When the data goes somewhere, it should be protected during transport, yada, 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 yada. So this is a defense in depth around data, right, from data security perspective. And I really like to compare this image with this one. If you don't know, this is an ocean cable, so the cable that lies in the ocean, right? And the data is only these small things, small orange things, the small orange wires. All the other layers, these are just protection layers. And this is how I like to look on the data security. We have a little bit of data and we have all these protection layers, because in some environments, these layers, this what keeps your data safe. And of course, you are security engineers, you know all these traditional security controls, you know all these application security controls that you can use. If you don't, I really recommend you reading NIST 80053, which has a list of security controls for your inspiration. They have like a tables that you can scroll and read about different security controls to implement. So what I wanted to emphasize here, that except of nice and shiny cryptographic technologies and cryptographic approach, we still need to use the traditional security controls around data, especially for risky, for high priority attack vectors. And we need to make sure that when we are building system, it's like an internet cable. It has all this overlapping and supporting each other security controls, right? Let's get back to our iceberg picture. No more monsters, no more monsters. We can use all this nice and shiny modern cryptographic technologies only after everything else is working. So requirements in MSS, in regulations, etc., tip of the iceberg. Different cryptographic approaches, application level encryption, end-to-end encryption, like going deeper. But everything will work if and only if cryptography is surrounded with a proper security controls. I hope you still have energy to move with me into cases. I don't know if it was too complicated, not too complicated, but let's continue. So what I will tell you right now, depending on the time, I might cut one of the cases. Yeah, probably I will cut CRDT one. It will be still available in slides, but still. So what I want to show you is the combination of different encryption approaches, like in real applications, in real products. For example, number one, imagine that you have software as a service platform for B2B, like for other companies. Why would you use encryption? Why would you use security? Because you have all these customers, like other enterprise customers, and they want to make sure that their data is encrypted, preferably using their keys, and that your employees don't have access to the data and other customers don't have access to their data, right? So you would like, it's a good applied it's a good application for encryption in large SaaS platforms. You would like to minimize the life cycle of data, like to make it in plain text as less as possible. There are different techniques available for that. For example, if you use MongoDB, take a look on client side, field level encryption on MongoDB. Remember we discussed, right? Client-side encryption is application-level encryption happening on the client application. Field level means that you can determine which fields to encrypt. So MongoDB has SDK that allows you to implement. You just drag this SDK into your application and you select which fields you would like to encrypt, and the application will communicate with Key Vault and communicate with Mongo and store encrypted records. Right, so in your MongoDB, you will have a mix of plain text records and encrypted records because you just selected to encrypt some of them. In a MongoDB case, they use the following key hierarchy. You have fields. Fields are encrypted with DEK, data encryption key. The data encryption key is stored in Key Vault or KMS and can be encrypted with customer master key. Customer master key typically stored in KMS. Sometimes this is not your KMS, but customer's KMS. This is key hierarchy typical for MongoDB, but they support different options. Just check. I put the link here. Just check the logs. When this approach is super useful when you use MongoDB, obviously. They also provide you with deterministic or non-deterministic encryption, means that they support search. They support searchable encryption. Yes, with some caveats, with some limitations, but still. What else? Where this approach might be not super useful for you, because this makes client applications kind of responsible, or at least to share part of responsibility for encryption decryption, just to have this cryptographic code from Mongo SDK, right? And partially for key management. So the application have access to key material, have access to the keys. In many cases, you would like to avoid that. And as examples, you can see you can push encryption from client side. For example, on proxy side or on DAO side, data access object, you can build encryption layer right outside of your application. In this example, we have the open source tool Accra, right? And this is our encryption decryption proxy. So your application connects to Accra, Accra connects to the database, and you define in Accra which fields to encrypt. It will work for SQL databases, for example. You define which fields to encrypt, and Accra will encrypt fields before sending them to the database and decrypt it when the fields are read from the database. And in this example, you push all the key management, all the security to Accra. Application has no idea that the data is encrypted. The database has no idea that the data is encrypted. And again, in the database, you will have a mix. Some columns will be encrypted, some columns will be plain text. That's fine. Accra uses a little bit more complicated key hierarchy for more flexible key rotation. In Accra, for example, each data field that you select to encrypt will be encrypted with different symmetric key. And those symmetric keys, data encryption keys, DEX, will be encrypted with key encryption keys that can be symmetric or asymmetric. Those key encryption keys usually stored in a key vault, in an intermediate key storage. They are encrypted with customer master key that is stored in KMS. So the key hierarchy is a little bit longer But as I mentioned, it's more flexible for key rotation because you can do things like key rotation without data encryption. Pros and cons of this approach. The good thing is that you can move your encryption from the application side, right? You can build all this key rotation, revocation, bring your own keys, things like that. And what is the trick? That when you have the single layer responsible for encryption, you can add other security controls there, like anomaly detection, like firewalling, like data leakage protection, right? So you can build like, you can divide your data flow into, we have plain text data here, less trusted, and we have encrypted data here, more trusted zones. Let's see, as example, no-code platform. No-code platforms is a SaaS application that allows their customers to build applications without code. Obviously, there is some code there, but the main idea there is that this is a huge SaaS that allows their customers to build apps. Right, and again, we have this problem that SaaS wants to protect the data of each customer using their own keys to isolate this data, to compartmentalize the data. And they decided to integrate encryption, basically to integrate encryption together with the data access object with DAO. So in reality, they use HashiCorp Vault. In reality, that the APIs access to data access object that is responsible to what data to encrypt, where to put this data, which keys to use, yada yada. So this DAO was called in HashiCorp Vault for encrypting, decrypting data before storing it to the database. And again, the data flow was divided into, here we have data in plain text, here we have data encrypted. This approach allows to isolate, to compartmentalize access, to show to their customers that, we will use your encryption key and all your data will be encrypted with your encryption key. And it's your responsibility. If you lose your encryption key, sorry, you might lose the data.
2 minutes.
Also, that as we mentioned previously, the cryptography works better with surrounding security controls, with supporting security controls. So in their case, at their SaaS platform, API platform for others, they did emphasize on API protection with all this anti-throttling, anti-fraud, access controls, yada, yada, with all this alerting. So they were telling their own customers that, it looks like your users behave maliciously. Another example, very similar, fintech. That was a huge application, really huge one. A lot of services, a lot of databases. So what they did, they used the same pattern. They pushed application level encryption into the single layer, into of course, with all this load balancing and all the things. And they controlled encryption from data access objects. So their applications, like API application, had no clue that the data is encrypted somewhere. The databases as well had no clue that the data is encrypted. The idea here is similar. In this zone on the left, data can be in plain text with TLS and all the things. On the right part of the zone, data is encrypted on a field level. Very easy to manage. And in a fintech, in case of fintech, they also had a special use case with BI analytics, right? So they needed to have access to the data to build analytics. So in this example, this layer did decryption and anonymization data, especially for BI software. And as I mentioned previously, there are several security controls used to support their platform. In that case, at their fintech, they used a lot of PCI DSS required controls like audit logging. Okay, let me wrap up. In the slides, you will see even more cases about ML encryption, right? How to encrypt ML models. By the way, the approach I describe is HPKE, hybrid public key encryption. This is really nice. I have a link here. ML protection is a very interesting one. Then, in the slides, you might see the encryption, end-to-end encryption for CRDT-based application, right? Which approaches to use, and if you don't know what is CRDT, again, a lot of links for you available. My favorite slide about different security controls that should surround cryptography. Yes, if there is like one slide for you, one message for you to take away from this presentation is that encryption is not that hard, you know. Key management, yes, key management is a little bit harder when you try to build in this in a data architecture in your real infrastructures. That's also a little bit of like a burden, a struggle. However, what is essential is this realistic orchestration of cryptography, key management, data flow controls, and all these traditional application security controls. And here, where it gets real. So that's it.
Cool.
Let's move to the questions.